Hi. In the previous video about spline and curves, what we've studied was the Bezier curve. And when we started to extend the Bezier curve to do a spline and to attach several Bezier curves back to back, what happened is that we were sharing the first and last point, and we were only sharing that one. So we had a discontinuity in our curve. If you remember this shape, we had here the first point, basically the tangent going in that direction for the first Bezier curve, and then the tangent we want to get it to go in this direction for the second tangent, so we don't have that discontinuities because we have different angle here. It is quite annoying to compute every time to make sure that you know that your previous point and the next point would actually be on a line, so you have continuity inside of your curve. And so for this, what we would do is, instead of parameterizing our curve using the 4 points, what we want to do is to be able to parameterize it using only the first and the last point, and then giving directly the tangent we want to use. So saying I want it to go in that direction, and then the second point will go in that direction, and we will be sharing that point and tangent to the next one. And that's allow us to more easily make sure that we have continuity between those stuff. So this type of curve now is what we call an Hermite curve. And the Hermite curve is basically defined as this, is defined as the endpoints and as the tangent, so basically as the derivative of the endpoints. So we now have the points and the first derivative of those points as the value we want to give to our function. Before being able to compute this, what we will have to do is to understand how we could do it just doing polynomial, and we will start from those mathematics, and then we will build the Hermite curve after it. So if we want to fit a polynomial through a certain set of points, you could actually fit any type of polynomial of a certain degrees to the number of points degree n plus 1. So if I have a cubic polynomial, I can fit it to go through 4 points. And again, as we were doing cubic mainly, I will focus on those cubic. So let's say that I will have, in this case, if it agrees to do it, I have those 4 points, and I want to define a curve, a cubic curve that will go through those 4 points. How we do this is that we start from the cubic function. And the cubic function itself, you know, is the at cubed plus bt squared plus ct plus d. So that's a cubic functions, the generic form of the cubic functions. So what do we know from the points we actually want to match? We know that when my function is at t0, the value will be 2. When a function is at t1, the value will be 1. At t3, the value will be 4, and at t4, the value will be 1 again. So I can have those as the values I would want to compute. And now what I can do is that I can actually substitute the 0, 1, 3, and 4 through these functions, which give us that d, because all the zeros will make everything disappear, d equals 2, and then here everything will be 1, 1, 1. So a, b, c, and d, a plus b plus c plus d equal 1. And then the cube, 27, 9, 3 plus d equal 4. And same for 4, 64, 16, 4, and d equal 1. So that gives us basically a system of 4 equations and 4 unknown. Now that's something we could easily solve. And so I will just put those equation in the matrix form, and basically I have the 2, 1, 4, 1 equal my big matrix coming from here. The D comes from the first one, A, B, C, D, 1, 1, 1, 1, 27, 9, 3, coming the next line, and so on and so on, and I get the A, B, C, D. And now that I have my matrix form, I can actually solve for A, B, C, D. And to solve through A, B, C, D, what I will do in this case is just use the linear algebra solve method from NumPy that will just solve this for me. And in my case now, I have the A, B, C, and D parameters coming from the cubic. And if I replace A, B, C, D with those values, now I can actually have a function that will go through my 4 points. So that's how you compute this kind of polynomial. Now that I have this and we understand how we could actually use the system of equation and to build them and having our functions or polynomial goes through a bunch of points, what we can do is we can start to look at the Hermite curve definition itself. And to start with the Hermite curve, what we will have to do is basically remember that we will be doing cubic Hermite curve again, same way. And so I'm starting from the cubic function again, so AT plus BT squared plus CT plus D, and I will just rewrite them this as a matrix form. So it's basically exactly the same thing, except that I've put them in a matrix form, but it's the same formula. Do not worry about this one. And what we will be doing now is again do as usual as the Bezier curve and all of that kind of stuff. We will say that the Hermite curve is parametrized between 0 and 1. And that will make our life way easier. Now we could do an interpolation saying that at time 0, we will be at point 0. At time 1, we will be at point 1. And then at time 0, we want to have the derivative of point 0. And at time 1, we want the derivative of point 1. So what happens when we do this is that we actually compute also the derivative of our function. So that's my cubic functions, and that's the derivative of the cubic function. If you don't remember, you take the derivative, you bring the 3 in front and do -1. So I get 3AT squared plus BT plus C, and the D disappear. So that's the derivative itself. And now, the same way as we've done when we were doing the polynomial, what we could do is substitute the different values for the different A, B, C, D. So I will have point 0. It's again, everything will be 0. So 0, 0, 0, 1 for D. At point 1, everything will be at 1. And then I will have the derivative of the point 0. Again, I will put 0 in these functions now. So everything disappears except the C. And I'll have the derivative at point at time 1, and then I will have 3, 2, 1, and 0. The D has disappeared. So basically now I have the same system of equation as we had before, except that now it takes point 0, point 1, the derivative of point 0 and derivative of point 1. And then we could solve for A, B, C, D again, except that this time I will not solve it numerically because I'm still trying to find the functions itself. So I will solve it by how we actually solve this kind of system usually. And to solve for ABCD, what we do is that we take the inverse of the matrix in the middle. So if you take the inverse of the matrix, now ABCD equal the inverse of the matrix, that's my -1, multiplied by the point 0, point 1, and the both derivatives. And if I compute that inverse, so that's my matrix, compute the inverse, I end up with this matrix. So I could actually write it in the function directly. I get the ABCD equal that matrix multiplied point 0, point 1, derivative and derivative. And now we have our ABCD here. What we could do with that is that remember that we've wrote the ABCD, the function itself as a matrix of times multiplied by ABCD. So I can substitute the same way again, my ABCD, remove it completely, and only keep the times, the matrix in the middle, and my points, so 0.0, 0.1, both derivative. Remember this formula, this shape is really close to the one we were using when we said that we want to do matrix form for Bezier curve. See, that's the same, except that the matrix is different, and here we used P1, P2, P3, and P4, but basically it is the same concept. Now that is 0.0, 0.1, and both derivative. What we have here is the formula if we were actually computing everything. Again, you get the 0.0 multiplied by this, 0.1 multiplied by this, the derivative multiplied by this, and the derivative multiplied by this. And that gives us the Hermite curve, and I can now see I've used the formula, the one I've computed here, not the matrix form. I've computed the formula, and I've used 0.0 2 times cube minus 3 times squares and all that kind of stuff. And you could see that basically it works now. I have my points, my derivative, I get the curves, and I reached here my point towards my derivative. That's a 1D example. So for 0 to 1, I have 2 values. And I can do the same for a 2D example. So instead of having a point that's just defined as t at the bottom and having a value for y, I can have an xy point, an xy point, and then my t, my parameterized 0, 1 will give me the curve the same way we did the Bezier curve. And you can see now what we have here is a 2D example. So I have the direction in which I want the curve to go, and I get the curve to go through my parameters, my 0 to 1, and it's in a 2D space. And that's what the Hermite curve is computing. Now there is, of course, as we define the Hermite curve, we said that it's another way to compute a curve that goes between points and have tangents. There is a link between how we computed the Bezier curve and what we're doing here with the Hermite curve. And basically, the formula to go from one to the other is if you have a bunch of Hermite, so you will have 2 points, the point 0 and point 1, and you get both derivative. To get back the 4 points of the Bezier curve, the only thing you do is that you take the first point as being the first point, the last one as being the last one, and then point 1 of my Bezier curve is point 0 plus a third of the derivative of point 0, and point 2 is the point 1 minus a third of the derivative. That divided by 3 will come in logically a bit later when we talk about a few the stuff, but right now just remember that we divide by 3 to get the right point in this case. So to show you that it works, what I could do, it's basically starting from that 2D example again. I have my 2D example, I have the Bezier, I have the Hermite curve, that is the black one. And so by using the Hermite curve now, I can actually put my points here, see that's a third of my derivative, and I get the points there for my second point, and the third point is a third of the derivative less, and I get my point here. And that's the Bezier curve, and that's the blue dot. And you can see that they're perfectly aligned. So they both are computing exactly the same thing, just a bit differently, again, on how you do it. And now if I want to do an Hermite spline, so I want to actually put a bunch of Hermite curves back to back, then I can just share not only the last and the first point, but also the tangent, and so I will have a continuous function instantly. What I will do is I will rearrange a few of the parameters, because when we built the matrix the first time, when we said it was 0.0, 0.1, first the derivative of 0.0, derivative of 0.1. But if I want to share the data between a bunch of curves, it would make more sense if in my data I had 0.0 derivative of 0.0, 0.1 derivative of 0.1. So I can just move forward inside of my list of points and derivative, and I can build a spline this way. So this is what I've done. I've used the matrix form, except that I've swapped the column. So I will get a point, derivative, point, derivative, point, derivative, and I can just directly reuse this to have a complete list. To have a list of spline of Hermite curve that goes back to back. So if I define now my list of points as a point and a derivative, a point and a derivative, a point and a derivative, I can have this Hermite curve that goes through a bunch of points. And so this was the video about the Hermite curve and Hermite spline. And in the next one, we will go through how to compute a bunch of stuff automatically to do what we call the cardinal spline that will make our life easier when we want to use Hermite curve. See you next time.